All right, this is to finish up the video for 1.2 notes. So we are right here on simplifying radicals part F. We're looking at the cubed root of 27. So we have to ask, is this a perfect cube? Yes, it is. The cubed root of 27 is 3 because 3 times 3 times 3 is 27. Now, once we get to G, we have a problem with our number inside. It is not a perfect fourth. Perfect fourths, if we look over to the side, are things that when you raise them to the fourth power, a base to the fourth power, we get an answer. So 1 to the fourth is 1, 2 to the fourth is 16, because that's 2 times 2 times 2 times 2. 3 to the fourth is 81, and that's going to be too big for our number since our number is only a 48. So if you encounter a number and you don't know what factor could possibly be a perfect root of it, a perfect power that we can use for the root, you just want to make a list of the factors. So 48 is 1 times 48. Then you asked us 2 go into it. 2 times 24. We can check that on our calculator if we need to. We would say, does 3 go into it? Let me share my whole screen so you can see my calculator. So 48 divided by 3 is 16. And I can stop here even though I know there's more factors, because this, as you're going down, these numbers are getting smaller and smaller. This one right here is a perfect fourth. So we can stop right there. So we're going to break 48 into the factors of 3 and 16. So I'm going to write this as 2 times the fourth root of 3 times the fourth root of 16. Notice that would multiply back to 48. And then a fourth root of x to the fourth. So the 2 is just going to come down. It's part of the answer still. Fourth root of 16, I'm going to go ahead and work that one out. That is a 2, because 2 to the fourth equals 16. Fourth root of x to the fourth, that's a group of 4, so there's just one of those. So fourth root of x to the fourth is x. And then I can't do anything with the fourth root of 3. That is not a perfect fourth. So my final answer is I multiply everything out front together. So that's going to be 4x fourth root of 3. So there's that one. Okay, for the next one, we're looking at just another base x again here. So 5, how many groups of 5 are in 7? There's going to be 1. So we'll pull out an x to the first for that group of 5 with 2 left over. So x on the fifth root of x squared. For the 12th, there is no, so if we look at our perfect fourths again, 1 goes into everything, but that's not going to help us because if you pull out a 1, you'll still have a 12. 16 is too big, so we can't do anything with the fourth root of 12. That's as small, that's as broke down as that can get. But we do have more than 4 x's here. So there are one group of 4 in the x to the 7th with 3 left over. So x to the first on the fourth root of 12x cubed. And then when we look at 100, this is perfect cubes. So I'm going to write a little note over here to the side, perfect cubes. So we have 1 cubed is 1, 2 cubed is 8. You can use your calculator to calculate these. 3 cubed is 27, 4 cubed is 64, and 5 cubed is too big, it's 125. So if you think about the factors of 100, none of these other than 1 goes into 100 evenly. You could check that, you could make your list. 1 times 100, 2 times 50. You can check 3 does not go into 100. Gives you a decimal answer. 4 times 25. 5 times 20. I knew that one. 6 doesn't go, 7 doesn't go, 8 doesn't go, 9 doesn't go, and 10 times 10. Notice if we look at any of these, none of the numbers in this list except for 1 are a perfect cube. So we cannot break this down. This is actually already simplified. All right, so let's do a few more that are like more variables and a little more complicated. So let's look at this one right here. 320, I'm looking for perfect cubes again, so I've got my list right there. So 1 times 320, then I'll divide 320 to see if it's divisible by 2 evenly. Oops, not 3. Well, we already know 3 doesn't work then. Divided by 2, that's 160. And we've got divided by 4. Need to check that. that's 80. Divided by 5 is 64. So right there is a perfect cube that would work. And that is also a perfect square, but it is a perfect cube when we're doing cubed roots. So we're going to break this down into the cubed root of 5 times 64. And cubed root of 64 is 4. If you look, 4 cubed is 64. So this is 4 on the cubed root of 5. Okay. Looking at cubed roots again, 16. We have 1 times 16 and 2 times 8. 8 is a perfect cube. So we're going to break that down into the cubed root of 8 and the cubed root of 2, because that multiplies to 16. I also like to break down my variables. I have a cubed root of x cubed, cubed root of y to the 8th, cubed root of z to the 4th. So I'm going to work out each of these individually. Can't do anything with cubed root of 2, but cubed root of 8 is a 2. So I have a 2 on the cubed root of 2. There are exactly one group of 3 in x cubed. So cubed root of x cubed is just x. This is connected by times. There are 2 groups of 3 and 8. So that's going to be y squared. A single y represents each group. So 2 y's get pulled out. That's for a group of 3 and another group of 3. With 2 left over inside. And then for this, there is one group of 3 and that's z. So a z to the first will come out for that one group of 3 with 1 z left over inside. So my final answer can't be all of this. That's really messy. We pull all the numbers that are outside and letters to the front. So I have a 2, an x, a y squared, and a z. And then we put all of our cubed root pieces back together. So I have a 2, a y squared, and a z. There is the simplified version of that one. Okay. Now for this one, we are going to need to simplify the 2 radicals first before we try and break out the pieces. If you break out the pieces first, you're going to have to multiply a lot of stuff back together. So let's just go ahead and make this one big square root. So that's going to be the square root of 18. A squared times a to the 5th is a to the 7th. B cubed times b to the 1st is b to the 4th using our rules of exponents. 18, and we're looking for perfect squares this time. So 1 times 18, 2 times 9. This is a perfect square. Okay, so I'm going to break this into square root of 2, square root of 9, square root of a to the 7th, and square root of b to the 4th. Okay, so we have a 3 on the square root of 2 for the number parts. 2 goes into 7. We have 3 times, so there's 3 groups of 2 I can pull out of the square root. And then a 1 left over. And this is square root again of b to the 4th. There's 2 groups of b exactly. So we'll pull out a b squared and no b's left over. So this is going to be 3 a to the 3rd b squared on the square root of 2a. Okay. For my part D here, 81 is actually already a perfect 4th. That is 3. 4 goes into 5 one time with 1 left over. Make sure you're putting the correct index on your root. And 4 goes into S to the 8th. It goes into that 8 2 times exactly. So no S is left over. So 2 groups of 4 get pulled out, 1 each. So remember, if you're trying to remember what we mean by that, it's the 4th root of s to the 4th and another 4th root of s to the 4th. Each of those gives us an s, which is why we get s squared. Okay. So hopefully that visual helps. All right, so that ends the simplifying radicals. The next way we simplify radicals, another way we can simplify them, is anytime we have a radical in a denominator, we want to rationalize or get it out of the denominator. So that means we multiply the top and bottom of our fraction by the same radical. It doesn't always have to be the radical in the denominator. We will determine what to use by what would make it a perfect power. And then that will eliminate us having a radical in the bottom, and then we will only have a radical on top, which is a more proper way to write your answer. Doesn't mean it's the only time we would want it. Sometimes we do leave radicals in a denominator for other reasons down the road, but when we're rationalizing, we're trying to simplify to a specific format. So if you notice this one, there's a square root of 5 down here. So if you multiply, it's a square root, so we need 2 of something to make it a perfect power. So I'm multiplying by another 5 under a square root so that I will have a 5 squared when I multiply them together. That is the purpose of doing that. And whatever we do to the bottom, we have to also do to the top. So this becomes a square root of 5 over square root of 25, because we multiply those two insides together since they're both in a square root and it's multiplication. And we can reduce that bottom because square root of 25 is just 5. Big thing to point out, this 5 and this 5 do not reduce because that is a square root of 5. That's actually a decimal answer, not a 5. Okay. So those, if one's in a radical and one's not, they do not reduce with each other. All right, let's look at another one. So I'm going to break this up into 2 radicals, one on top and one on bottom. They're both going to be square roots since the overall radical was a square root. That actually allows me to simplify the top before I even get started. So that's a 5 over a square root of 3. I still have a radical in my denominator, so I'm going to multiply by another square root of 3 so that it becomes a perfect square under my radical. Whatever we do to the bottom, we have to do to the top. So that's 5 square root of 3 over square root of 9. So that's 5 square root of 3 over 3. Okay, let's talk about my next 3 because these are where things get a little tricky. Notice this one is a cubed root on the bottom. So we don't want 2 of something, we need 3 of something. So I'm going to multiply by a cubed root of x to the first. The reason I'm using x to the first is because I want to make, when I multiply my 2 bottoms together, I want to make sure I have a group of 3. So 2 plus 1, since we're multiplying same base, would give me a 3. That is why I'm choosing this, not multiplying by the cubed root of x squared. That actually would make it still have a radical in the bottom. That's why I said you can't always just multiply by what's in the bottom. It depends on what the root is and how many do you need to make it make that equal grouping. So whatever we do to the bottom, we do to the top. So this is 2 cubed root of x on the top. On the bottom, we have a cubed root of x to the third. So I'm going to get just an x. Cubed root of x to the third is just x. So no radical left in my denominator. All right, let's talk about this one. So 9 is 3 times 3. So I have 2 3's right now. I'm going to need another 3 to make sure I have a group of 3 3's because we want a cubed root, a group of 3. I have 4 x's, so I actually have more than a group of 3, but I need something also to be divisible by a group of 3. So 4, if I pulled out my group of 3, I would still have an x left over. So I'm going to put in 2 more x's because that will give me x to the 6th, which is divisible by 3. It's the smallest group I can create where I will get an equal amount of groups of 3. Whatever you do to the bottom, you should also do to the top. So that's going to be cubed root of 3x squared on top because it's times a 1. On the bottom, I'm going to have a cubed root of a 27 and an x to the 6th. So we can reduce that bottom. Cubed root of 27 is just a 3. 3 groups of, 2 groups of 3 and 6. So that's going to be an x squared. And notice again, these do not cancel or reduce because this one is under the radical. Okay. All right, let's look at my next one. So I'm going to break this up into radical on top. Both of these are going to be square roots since the original root is. So I'm wanting to create perfect squares. So I only need 2 of things. Pairs or groups of 2. So if I get another 2, that'll be a group of 2's, a pair. And then I need 1 more y to make it an even pairing of groups of 2. So whatever we do to the bottom, we also do to the top. So it's like multiplying by a 1. So we multiply the top, that's going to be a square root of a 6 times an x times a y. On the bottom, I have a square root of 4 and a y to the 4th. So I have square root of 6xy on top and a 2y squared on the bottom. Now, a lot of times students will ask me, well, couldn't you have just done, since this is the square root, couldn't we have just done 2y cubed in both parts right here and multiplied by itself? Yes, you can, but you will create more work in simplifying. You will have stuff in the top of your radical that will need to be simplified. Notice nothing in my numerator needs to be simplified. 6 is not a perfect square and doesn't have any factors that are perfect squares, and x and y are both to the first power. They are less than a group of 2. If you had multiplied by 2y cubed on both top and bottom under a square root, you would have had a y cubed on top and a 12 on top as well. You would have had more than you needed on top, or not, sorry, it wouldn't have been a 12. It would have been a 6xy to the cubed. You would have had more than you needed on top, and you would have had to simplify that radical out. So the best and easiest way to get to the correct answer quickly is just to ask, what's the bare minimum I need to multiply by to make the perfect power for my root? So since I had 1, 2, and it's a square root, I needed another 2. Since I already had 3, which is more than I needed because I needed a group of 2, I just bumped up to the next group of 2, which would be 4. So 2, 4, 6. So any multiple of this root right here, 2, 4, 6, 8, for cubed roots, 3, 6, 9, any multiple of those works for the exponent part, okay? All right, and then the last piece of the notes for today is the properties of rational exponents. So a rational exponent is actually a radical expression as well, because rational exponents, which means fractional exponents, means that you have a radical. So anytime you see one of these, you actually have a radical. The way we convert it is the number on top is inside with the base. The number on the bottom is your root, your index. So this is the nth root. You can write this another way as well. You can do the nth root of a and then raise it to the power of the numerator. That's also okay. So I'll show you this one both ways. The nth root is our radical. The top part stays with our base, or if it's easier to calculate, we can do the nth root of a and then raise it to the nth power. These are both equivalent. It's just sometimes this one is easier when you're calculating with numbers, okay? This is something we've already practiced, breaking radicals up with numerator and denominator if it's a big fraction, and multiplying, we can break it up into factors. So just restating those properties. So this first example just wants us to write this using rational exponents. So remember, the root is your denominator. So this is going to be x to the 3/4 power. So there's the answer for that one. Okay. Rewrite using a radical. Now be careful with these. If this is not in parentheses, the root's exponent only goes to the base directly in front of it. So this first one would be 4. And then this is a square root, since there's a 2 in the bottom, of x to the 3rd. And again, I'm not asking you to simplify on this. It didn't say simplify. So even though I know I can simplify that x because there's more than 2 of them in there, they just said rewrite. So we're going to leave it like this. On this one, this is the whole thing is going to be under the square root. So it's going to be square root of 4x, still in a parentheses, raised to that numerator power. Okay. For this one, the 4 is not included in the radical, so it'd be 4 plus the square root of x to the 3rd. You can write your 2's in there if you need to see them. And then this one, everything's going to be under the radical. So this would be square root of 4 plus x. Notice I'm keeping it all in a parentheses, cubed. Okay. And again, if we were simplifying those, we could go further, but they just wanted us to practice rewriting it using the notation of radical. Okay. All right, so let's actually do some that might need simplifying. So the first thing I notice on this A part is there's a negative exponent right here. So I'm just going to rewrite this with that whole base moving to a denominator because the exponent is negative. I'm not moving this one to the denominator because it's not the exponent that's negative, it's the base. Only a negative exponent makes something move. So that's going to be a 4, and then it'll be to the 5/2 now. Okay. Convert these to radicals. This would be cubed root of negative 27, and I would apply the power on the numerator after doing this because I can actually take the cubed root of negative 27. I don't want to square negative 27 and then try to figure out the cubed root. That'd be a lot harder. So square root of 4 and then raised to the 5th power. That's why I showed you that alternate form of writing this either with it inside or with it outside on top of the whole thing. So this is cubed root of negative 27 is negative 3. We're going to then square that. Square root of 4 is 2. We're going to raise that to the 5th power. So this ends up being 9 over 32 if you get your calculator out. Okay. For this one, we can apply this and turn it into a cubed root, or we can use our exponent laws. If you use the exponent laws, you'd be doing r squared to the 1/3 and s to the 6th to the 1/3. You're just multiplying your exponents. So that's r to the 2/3, because 2 over 1 times 1 over 3, you multiply top times top, bottom times bottom. This would be 6/3. So that's going to be r to the 2/3 s squared. So that would be if we wanted our answer to be in exponent form. Okay. If my directions wanted me to write my final answer in radical form, then I would turn this into a radical. It would be the cubed root of all of that, since it's all in a parentheses, raised to the 1st power. So we want to see that this is truly the same answer. That's to the 1st power is still going to be r squared and s to the 6th. We can't do anything with the r's because we don't even have a group of 3, but I have 2 groups of 3 in s to the 6th. So I'm going to pull out s to the 2nd for the 2 groups. No s is left over, but I do have the 2 r's still inside. So even though you don't see it, this is the same thing. S squared and s squared, 2/3 is really a cubed root of r squared. So this would be if you wanted to write your final answer in radical form. So just pay attention to the directions. Did they ask for you to write your answer with exponents or with radicals? That determines if they want this rational exponent in exponent form versus radical form. Okay. And then the last one, I would probably move this y up first because it has that negative exponent. So x to the 6th, y to the 4th over 9. I have the whole thing to the negative 1/2. So remember, we don't like it when our outside is a negative exponent. We flip the whole fraction, make it its reciprocal, and that turns that into now a positive 1/2 for the outside exponent. Okay. So I moved this first because this was a negative exponent, moved it up to get rid of the negative exponent on the outside. We flip everything. And notice that doesn't change anything about the bases or their exponents when you do that move. It's only changing the sign of the outside exponent. And then we're going to take this is going to be square root of everything. So square root of 9 to the 1st, square root of x to the 6th to the 1st, because that's a 1 on top of that, and square root of y to the 4th to the 1st, which is still going to be y to the 4th. That's going to be 3. This is, remember, looking for groups of 2. So there are 3 groups of 2 in 6 and 2 groups of 2 in y to the 4th. So there's my final answer for that one. All right, hopefully this helps you finish up and start getting to work on that first homework assignment. Please let me know if you have questions. I'll start off by kind of talking about whether or not we have questions on this short video at the beginning of class on Wednesday.